All the complex analysis is fun. Some is just more fun than others. Okay, so what I want to do today is I want to talk about the method of stationary phase, or Laplace's method. I'm going to concentrate for now just on one special case. You can do this in much greater generality. Okay, so the goal here is to give you a sense of what methods exist. So today we're going to concentrate when the entire quantity is real valued. I'm trying to decide on Friday if I want to actually go into what happens when you have a complex amplitude. You can generalize all of this. The goal is for you to be aware of what's out there in the literature. And so what I want to do is I want to go through the book's proof. So you were supposed to read the book's proof carefully for today in the Laplace method section. I think there are, because this is being recorded and I know the two authors, I think it's a well-written section and it's written like a math paper, where a lot of the details are not done in great explicitness. And they basically just say, this is going to be small, this is exponential decay and whatnot. So the framework is there. But going through and actually chasing it down and putting all the stuff, that's going to require some work. That's what I want to concentrate on today. So the goal is to consider something of the form, the integral from a to b, e to the minus s, and I'm going to go capital phi of x, c of x, dx, as x goes to infinity. For today, we're going to assume s is real. So as soon as I write s is greater than 0, not only is it real, but it's positive. Later, we can talk about what happens if s is complex, and this could be understanding Fourier transforms. So if you're going to do this, you need to have some conditions on the various things. We're going to assume phi and c are nice. We'll assume phi double prime of x naught is greater than 0 in the interval ab. We'll assume phi has a minimum at x naught, which will be inside ab. So it's very important that we're assuming right now that it's inside ab. You could, of course, modify the discussion if it's at one of the edges. It's going to mostly bring in a factor of 2 difference. All right, so let's try to think what's going on. So this is a lost art. I will risk trying to do this. Curve sketching. So if I tell you phi double prime is always positive, what does that mean about phi prime? So phi prime is increasing. Okay. Do we know the value of phi prime? Okay. We do know that we have a minimum at x naught. So here's x naught. We have some minimum. Is it possible we could have a minimum someplace else? Phi prime is strictly increasing. So it's got to look, we don't necessarily know what it's like. But because we have a minimum here, it's got to be coming down and then going up. So what that means is if it's coming down like this, the first derivative has to be negative right before this. And then it's going to be positive afterwards. And since phi double prime is positive, it's always going to be. Now over here, we know the first derivative is increasing. So that means it's becoming less negative. So that means the first derivative has to look like this going all the way down. And so by just doing something like this, we get a quick rough shape of what's going on. So we're only going to have one minimum of phi. If you think about what's going on, near the minimum of this, the exponent here is going to be as small as possible. S is going to infinity. So if you evaluate this at any place other than the minimum, there's going to be a huge difference in the value of the exponential. So almost all of the contribution should come from x very, very close to x naught. How do we determine the scale? So contribution from x close to x naught. How do you think we measure the scale? What do you think it means for x to be close to x naught? So what's my only parameter that can somehow control the scale? S. It's got to be close to x0 with respect to s. Or maybe 1 over s. And so it's really going to matter, how phi of x is changing. So if phi of x changes by 1 over s, then the change is going to magnify only by a factor of e. So it'll be on the same order of magnitude. But if it changes by 1 over square root of x, square root of s, then that's going to be like an e to the square root of s more, and that should be a huge change. So this should give you maybe some idea of roughly how far we expect things to be. We expect almost all of the contribution from the integral to be from that one point. Without loss of generality, what should we assume for phi of x0? Zero. Right. Whenever I say without loss of generality, it's got to be something. Why? Well, if it wasn't 0, we could add phi of x0 and then subtract phi of x0. And if we add and subtract the phi of x0, we'll get an e to the negative s times negative phi. So we just pull that outside. Okay? So you want to get a sense of what you expect the answer to be like. All right. All right. So now let me try to write the statement. So we'll assume. Oh, it did not last long. Oh well. So we'll assume phi of x0 equals phi prime of x0 equals 0. We'll assume phi double prime of x0 is greater than 0 otherwise. And then the integral from a to b of e to the negative s phi of x c of x is equal to e to the negative s phi of x0 times the following. A over square root of s plus big O of 1 over s, where big A is equal to the square root of 2 pi c of x0 divided by the square root of phi double prime of x0. Okay. So I want to write it very carefully like this. The whole factor here is just because I want to write down the formula that holds in the general case when phi of x0 is not necessarily 0. That's what this factor is here. This is the main beef over here. This is the part that has the real action. I'm going to prove things a little bit differently than the book. I want you to get into pattern recognition. When you look at this expression, which parts here look good? So we've got 3 factors here. Can somebody give me a reason why you would expect at least one of them?
The phi double prime denominator.
Okay, why would we have that?
Because if it kind of gives an idea of how quickly the function is changing away from x0.
Okay, good. So this is going to maybe be related to how rapidly we're changing. What about the c of x0? Yeah, I mean, we think most of the contribution is near x0, and then this function c shouldn't really change that much in that region. And so if we're talking about x on a very small scale, we might as well approximate c of x with c of x0. So that seems reasonable. Square root of 2 pi. What do you think of when you see square root of 2 pi? Normalization. Normalization. Which normalization? E to the negative x squared. A Gaussian. So if you can look at a formula, you can get some sense of where the proof is coming from. So they don't quite go through the normal distribution in the proof in the book. So I want to tweak it a little bit. Why might we have a normal distribution? So let's look at our assumptions about phi. Phi of x0 is phi prime of x0 is 0. So if we expand phi of x, it's going to look like quadratic plus a small pollution. So we expect phi of x to be phi of x naught, which is 0, plus phi prime of x naught, which is 0, plus phi double prime of x naught over 2, x minus x naught squared, plus higher order terms. And we can write the higher order terms as 1 plus some small function phi of x. And I want to make sure they write it as phi of x or phi of x squared. There's two different ways you can write it. They want to write it just, they want to write it just as phi of x. Okay, not as 1 plus. With phi of x naught equals 1. And this is just coming from a Taylor series. So you can begin to see what kind of assumptions we're going to need about our functions to make this work. Yes?
Where does that expansion give us the Gaussian?
I'm sorry?
Like why does that?
Well, now let's think why this is going to give us a Gaussian. If we put this inside over here, we're going to have like a negative s x minus x naught squared plus a small pollution. If the small pollution doesn't really matter, if we just replace it with an x minus x naught squared, then we have an s upstairs that comes down as a 1 over s as the variance. And then that means it's extremely tight. So how many of you have seen a proof of the normalization constant for the normal or the bell curve? Okay, so since not everyone has seen it, let me just quickly go through and do this. So we say x is normal with mean mu and variance sigma squared if the density function is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. So this is the density of the normal. By doing a change of variables, it's enough to assume mu is 0 and sigma is 1, because you can just shift the variables. So I'm going to just handle that case. By doing a change of variables, you can actually write this as a gamma function. You've got to be a little bit careful. Instead of going from minus infinity to infinity, you go from 0 to infinity and double, because you have to do a change of variables u equals x squared. And if you go from minus infinity to infinity, well, if x squared is replaced by u, then u goes from infinity to infinity, and you're integrating just over a point. So if you want to go and write it as a gamma function, you're fine, and then you get that this is basically gamma of a half. And then you have to somehow figure out what gamma of a half is. We've talked about how to do it. The fun way is to say, let's let I be the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 dx. And I'm going to put in this square root of 2 pi because I already know the normalization constant. I've lost track how many times I've taught probability over the past 14 years. I can't pretend I don't know it anymore. So the trick is you square I, and you have 1 over square root of 2 pi e to the negative x squared over 2 dx, and then you use a different variable, e to the negative y squared over 2 dy. So this becomes the double integral, negative infinity to infinity, negative infinity to infinity, 1 over 2 pi e to the negative x squared plus y squared over 2 dx dy. And now, your Calc 3 comes back to you. Whenever you see a dx dy, you always think about either switching orders of integration or a change of variables. Why should we not switch orders of integration? Okay, I can't even ask you this with a straight face, right? They're completely symmetric. So we only have one technique left. We have to change variables. And since we notice that it only depends on x squared plus y squared, we try polar. And then in polar, this is the integral r goes from 0 to infinity, integral theta goes from 0 to 2 pi, 1 over 2 pi e to the minus r squared over 2 r dr d theta. Well, the theta integral is easy. It's going to give us a 2 pi, which cancels with the 2 pi. And then the r integral, it's really nice. The derivative of the exponent here is going to be 2r over 2 dr. Oh, good, just r dr, but with a minus sign. So the minus sign flips the order of integration, and we get e to the negative r squared over 2 at 0 and infinity, which is just 1, which is 1. So this whole thing equals 1. So now we know that I squared equals 1, so I is plus or minus 1. We're integrating the non-negative function. So I greater than 0 implies I is 1. So this is the standard proof of the normalization constant of the standard normal. Okay. Any questions about this proof? I still remember seeing this in my freshman year in my math class. It's a wonderful, wonderful idea that, to calculate this real quantity, you square it and, have the tools and techniques of multivariable calculus at your disposal. And in some sense, this fits really well with the theme of today and the theme of stationary phase. The section is not just Laplace's method. It's applying Laplace's method to a specific problem. Which problem are we going to apply Laplace to? So what are we going to use this to estimate later? What's the whole point? What are we applying this to? Not prime numbers. It's Stirling's formula. We're trying to apply Laplace's method to Stirling's formula and get some kind of asymptotic as n goes to infinity of n factorial, or of gamma of s, which is equivalent. If you think about this, the factorial function is initially defined on the integers. It's initially defined as discrete, but we expand our view and we view it as a continuous function. And then that gives us the tools of complex analysis and real analysis to use at our disposal. We're doing something very similar here. We're taking something that's initially in one dimension, we're expanding it and allowing ourselves to use more tools. So again, most of you are probably never going to use the method of stationary phase in the rest of your life, but just this idea of attack, that's what I want to highlight. All right, so what I want to do is I've broken the argument in the book down into 5 steps. And what I want to do is I want to carefully go through the 5 steps and talk about the details, what was missing, and how you fill it in. Okay, so step 1 is trivial. I've been told I'm not supposed to say that in mathematics class, but I am tenured. There are a few advantages. Without loss of generality, phi of x naught equals 0. And again, you can just go through and say, if I write this as phi of x naught, phi of x minus phi of x naught plus phi of x naught, and you just pull everything out. Okay, so that's step 1. That's not so bad. All right, step 2. We've already started step 2. They want us to say phi of x is 1/2 phi double prime of x naught, x minus x naught squared times phi of x, with phi of x naught equals 1 plus big O of x minus x naught. Is everybody comfortable with big O notation? Yes?
Oh, I thought you were asking.
Yes, okay. Is anybody not comfortable with big O notation?
I can use it after.
Okay, that's fine. So we say f of x is big O of g of x if for all x greater than or equal to some x naught, there exists a c such that the absolute value of f of x is thus equal to c times g of x. So for example, x squared is big O of x cubed as x goes to infinity. X cubed is big O of x squared as x goes to 0. 2x squared is big O of 1/2 x squared. And if you just take the constant to be 4, you'll be fine. So it basically means that the quantity on the left is growing no faster than a multiple of the quantity on the right. Left grows no faster than a multiple of the right.
So the C does not depend on the left.
Correct. But it could depend on x naught. So from your point onward, it's going to have this relation. So big O notation is extremely useful in keeping track of errors, of main term, lower order term, and telling you how much of a lower order term it is. Sometimes what you might do is when you have big O constants, you might actually put subscripts to say what's in play. So maybe I'm trying to compare log to the mx is big O of e to the x. And I might put a subscript m to indicate that the constant depends on the m. And again, the more elaborate your notation is, the longer it takes to type, but then you can quickly glance down and see what's in play. And sometimes when you have problems, you might need to understand how these big O constants vary as you vary the parameter. Maybe you're changing the degree of the polynomial as things go along, and you will need to know how these coefficients change. So there's a lot of analytic number theory papers where you have to do a great job keeping track of all the quantities. Fortunately for what we're doing here, there's not that many things that are going on. Okay, so any questions about step 2? So this is basically just saying that phi has at least a second order Taylor series expansion. And actually a little bit more, maybe a third order Taylor series expansion. So assuming a nice expansion for phi. This is not a horrible constraint in practice. If we're trying to evaluate these integrals, phi is often a nice integral. And I don't see any point in trying to get the most general theory right now. In the applications we're going to need, phi and c are going to be nice functions. I have not said anything yet about the integrability of c. And I'm being deliberately vague on that. I want to see organically what happens as we start doing the calculations. The other thing is, in terms of a normal, if we go back over here, we see that, oh good, it does swivel. We see that it's e to the negative x minus mu squared over 2 sigma squared. So what we had over here, we had a s. We want to have some quantity squared divided by 2 sigma squared. Well, if you look at the Taylor series, we've got a 2 coming right here. We've got a phi double prime upstairs with an s. The phi double prime s should be coming downstairs. And you should basically get like s phi double prime should be your sigma squared. Oh, square root phi double prime, square root of s. Right? If you look at it, you can begin to see the Gaussian coming into play. This is why I prefer this method of argument, and you're highlighting the Gaussianity. Let's see if I can get it to swivel. No. Can you just swivel it? Thanks. OK. So now let's go back. Thank you. Now it's detecting. It doesn't like it when I go that far over. I feel very confined. Are we happy with step 2? Yes?
So does the O of x minus x naught, is that like the third order and above terms?
Exactly. Is that all the higher order terms will have an x minus x naught cubed, 4th, 5th, 6th, 7th, if you want to assume phi is analytic and is given by its Taylor series expansion. I can give you horrendous functions like e to the negative 1 over x squared if x is not 0, and 0 if x is 0. And this function is not given by its Taylor series expansion. But we would have, I think, something like this would hold. So we're just assuming we can expand out phi. OK. So step 3 now is trying to replace and change variables. So we want to change variables. Well, based on the fact that we want a Gaussian, the change of variables should be obvious. We don't want to do too much with that 1/2. Even the phi double prime is fine. That's just going to be coming in to the variance. So this quantity here should be our y squared. So it suggests that we should choose y to equal x minus x naught phi of x to the 1/2, or square root of phi of x. Now, of course, as soon as you see a square root, you should be a little bit worried. So how worried are we about the square root? Because I want things to be continuous. Are we worried? So what's the danger with the square root? Yep.
If it were negative.
Yeah, if this quantity were negative, we could have trouble. Or we could have trouble if we have to worry about which sign of the square root do we want. Do we have to worry about this quantity getting negative? No, why not?
As long as we're near x naught.
Good. As long as we're near x naught, phi of x is going to be very close to 1. And so actually I probably should write this as phi of x, not phi of x naught. And phi of x naught would be identically 1. So as long as we're near x naught, we're going to be fine. We're not going to change which branch of the square root we're on. So this is a really good change of variables. And if you think about what's going on now, before we're integrating from a to b, we're now integrating from maybe a little bit negative to a little bit positive. Because when you put in x equals x naught, you'll get y equals 0. A little bit above x naught, y is positive. A little bit below x naught, you'll get negative. So y goes from negative to 0 to positive. And it's 0 at x naught. So just trying to get a sense of what's going on, we can begin to see this will look like integrating a normal. And if you're integrating a normal, if you want to get most of the mass, you want to integrate from 0 a good way down. So for me, I really want to keep thinking normal distribution, normal distribution, normal distribution, normal distribution. And that, to me, is the motivation behind all the calculations. All right, I'm going to erase big O. OK, so now we have some more stuff in step 3. dy dx. So the first thing is we want to calculate how much is y changing at x naught. And I claim that this is 1 plus something small. I think I want to write it 1 plus big O of y. So what am I doing right now? I'm doing dy dx. They want it at x naught to be 1. OK. Well, if we take the derivative of this, we use the product rule. The derivative of the first piece is going to be 1. And then we multiply by phi of x naught, which is 1. And then we have this times the derivative of this piece. The derivative of this piece is going to be well behaved. You'll have 1/2 phi of x to the negative 1/2 phi prime of x. Well, since phi of x is close to 1, in the denominator it's going to be fine. And then when we put x equals x naught, this piece will kill it. So the derivative is going to be of size 1 plus big O of x minus x naught. So it would be 1 plus big O of x minus x naught. And then if I actually evaluate it at x naught, I would get 1. So that gives us dy dx. We want to get dx dy. Well, I have this expression over here. I can take the derivative of both sides with respect to y. So take derivative of relation with respect to y. And so if we take the derivative of this relation with respect to y, we get 1 minus, now the derivative of this with respect to y would become, 1 equals dx dy times the square root of phi of x plus x minus x naught. And now we have the derivative of phi of x with respect to y. So we would have square root of phi of x down here. We would have a 1/2. And then we would have a phi prime of x and then dx dy. Well, for x very close to x naught, this is going to be very small. Right? And so when the dust settles, I claim we get dx dy is going to be 1 plus big O of y. So the question is, how does y compare to x minus x naught? So if x minus x naught is of size epsilon, how big is y? Also of size epsilon. There's going to be some small changes because of the square root of phi of x. But if x is really close to x naught, whatever that order is, that's basically the same size as y. So if I want to try to understand what's going on here, I've got the dx dy, I've got 1 plus blah. And I can bring the 1 plus blah over to the other side. And I can expand using the geometric series. So I would get, I have 1 plus blah, I expand, I get 1 minus blah, 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 right? So what's the square root of phi of x? That's very close to 1. It's going to differ by something, again, of size big O of y, big O of x. They're all the same. And so when you go through the algebra here, you get dx dy is going to be of size 1 plus big O of y. And so this is the relationship we want to use as we're doing the change of variables. Okay, any questions over here? All right, so the book says there's one more part to step 3 that we need to do, is we need to figure out how c is changing. And so the whole thing is we're trying to set ourselves up for a change of variables. So we start off with the c of x. And we're going to replace this with a new function that's going to be very slowly varying. We're going to replace this with some function c of y. And we'll put a tilde on it to indicate that it's a new function, but it's related very closely to the original function. And then the claim is that this should be c of x naught plus big O of y. And if you think about what's going on with this, big O of y is not moving that much. Y not moving that much is equivalent to x not moving that much. So if we change here, c of x, well, this should be, c of x naught plus c prime of x naught, x minus x naught, plus dot, 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 dot. We have a nice one-to-one relationship between y's and x's. We have a nice change of variable that we can do. So rather than evaluating a function c at x, we can evaluate this new function c tilde at y. And then we just have this really nice conversion factor. You give me a y, I can find the corresponding x, and then I plug that into c of x. And because we have this expansion like this, and this piece over here is of size big O of x, which is big O of y, we have this expansion here as well. That there really isn't much harm in moving y small amounts. Okay, any questions on this part? So this is all the preliminaries. This is finishing up step 3. All right, so now we're ready for the real nitty-gritty stuff. All right, so what we want to do now is we want to choose a small interval and a point in that interval and evaluate what's going on. So this is where more blackboard space would be fine. All right. What I think I'll do is I think erase this and just write the relationships we have. So we'll write dx dy is 1 plus big O of y, and we'll write c tilde of y is c of x naught plus big O of y. And this will free up some blackboard space. Okay. So consider an interval, and I think they use primes. I would rather use alphas, but I think they want to use primes. All right. Consider an interval, okay, a prime, b prime, contained in AB. What point do you think we want to have in the interval a prime, b prime? Yeah, it's the point where all the action is happening. So this corresponds to an interval for y. So it'll correspond to 0 being in some interval alpha beta. Well, I guess we'll do it with closed endpoints. With alpha less than 0 less than beta. And now what we want to do is we want to integrate from a prime to b prime. And I think we're going to be our original function, e to the negative s phi of x c of x dx. Okay. So there's a claim in the book as to what this equals. But before we do that claim, why don't we look at what we're truncating? So if we do this, we're missing some parts. We're missing the integral from a to a prime of e to the negative s phi of x c of x dx, and the integral from b prime to b of e to the minus s phi of x c of x dx. So this is the part that the book skips. So we need to figure out how much can these integrals be. And this is where it would help to have some information about c. And the book doesn't really say that much about c. But we know we are staying a sizable distance away from the minimum. So if you think about what's going on here, we're going to have enormous exponential decay. So we'll be okay if c of x has modest growth. Now the problem is, in one of the examples we care about, Stirling's formula, c actually blows up at one of the endpoints. So we need general conditions so that these things are fine. So for instance, if c of x is bounded, then these integrals are going to be small. Because since this is bounded, this is an exponential function. As s goes to infinity, c of x is going to be of modest size. This will eventually become completely negligible. Remember, these numbers here, maybe we'll be looking at positive, we've got a minimum is 0. This is always going to be greater than 0. It's got to be at least a quadratic, so there'll be some reasonable growth in x. And with that reasonable growth, we'll be fine. How fine will we be? Well, if you look at what's going on, the main term over here, I was trying to go here but not too far. Go a little farther. All right. So if you look over here, our main term, we have a e to the negative s phi of x naught. At the other ones, we'll have at least an e to the negative s phi of maybe a prime. And as long as there's a sizable difference between them, that'll be a huge exponential difference between them, and it'll be a lot lower order term. So what I would like to do now is, rather than doing the most general case, is say we will restrict to function c such that these integrals are small. And then whenever we apply the method, we need to just check and make sure these are small, rather than deducing the most general cases. So need these small. Boundedness will be fine. In the Stirling application, I believe c of x turns out to be 1 over x, so it's blowing up as we get near 0. So we'll have to do a little bit of work, but it won't be too bad. The idea is we should not be expecting much from these, because we are so far away from the minimum value that we're magnifying it enormously. So imagine the minimum value is 0, and now we're at 1 over a billion. Well, you might think 1 over a billion is pretty close, but you can take s to be a billion to the 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 billion a billion times. And when you do that, the fact that this is 1 over a billion is now magnified so much that the contribution is just negligible relative to what's going on near the main point. That's the whole issue, is that because s is so large, as soon as you have phi of x getting a little bit away from 0, from its minimum value, it's just damped to negligibility. All right, so do we all agree that in the cases we'll have to check, but that this should not be a problem? That, reasonable decay, it now comes down to this integral over here. Okay, well now if we want to do that, now we do our change of variables. And so the integral from a prime to b prime e to the negative s phi of x c of x dx, this becomes approximately, all right, so the book does a few steps all at once, which we will slowly unwind. Integral from alpha to beta e to the negative s phi double prime of x naught over 2 y squared dy plus big O integral from alpha to beta e to the negative s phi double prime of x naught over 2 y squared absolute value of y dy. Okay. So let's see what's going on here. There's a lot of approximations that are going on. The first is we're switching from x integrals to y integrals. All right, well, if we're switching from x integrals to y integrals, the a prime, b primes go to alpha, beta. So that explains what's going on here. The phi of x, the phi of x is going to basically become our y squared. But remember, when we chose our definition of y squared, we did not include the factor of 1/2 phi double prime. So we have to keep the 1/2 phi double prime, and then we have y squared. We need the Jacobian calculating going from dx to dy, but we know that the error in that, the Jacobian is basically 1 plus an error on order of y. So this is where we're now using the change of variable formula. That's why we're calculating the dx dy, dy dx. Most people forget which way it goes. You can always rederive it, or fortunately, if dx dy and dy dx are both 1 plus something small, it does not matter. And so we don't have to really worry about getting the formula exactly right. We just have to be approximately right. I can do approximately without too much trouble. So we know that we can go from dx to dy with an error at most big O of y. That's what this part is coming from over here. This is the main term, and this is the error term coming from the big O of y in the dx and dy interchange. Is there anything else we have switched? So this is coming from the Jacobian. Anything else we've switched in this step from here to here? We've done two things. We did dx to dy. What else did we do? There's one other thing we did. Well, the bounds come from the change of variables. The bounds come from the change of variables. But there's some other place where the change of variables comes into play. It's not just in the dx, it's not just in the bounds, it's not just in the phi. There's one other place where the change of variable has an impact. It's the c, right? The c becomes a c tilde of y. So we need to also go, that's a horrible A, also c of x goes to c tilde of y. But c tilde of y is essentially c of x naught plus a small change. How much is that change? It's also, again, of size absolute value of y. So when we're trying to figure out what the contribution is, we have two errors that come like this. Should there be an error of size absolute value of y squared, maybe when the two errors hit each other? Probably. Why am I not worried about an error of size y squared?
Because y small.
Yeah, y small. And so y squared is dominated by y. And so in this region, we are very, very close. Y is very close to 0. So now we're left with these two integrals. Okay. Any questions as to how we got here? We're comfortable with steps 1, 2, 3, and 4. So now all that's left to do is to evaluate the integral. And so if we have the main term and the error term. Okay, this is the main term. This term is going to be smaller. And the claim in the book is smaller by a factor of 1 over square root of s. Some of you might even remember a problem like this from a probability exam many years ago, in terms of just how these things change. Does it make sense that this integral should be smaller than this integral? And if we think about what size do we expect y to be? Well, looking at this, again, I always want to think of what's the natural scale. Once y is 1 over square root of s, that's going to be the same size as this. This will be something of the size exponential of a constant. So I expect y to get as large as 1 over square root of s. Once y is much larger than that, the exponential is going to be so large it's going to be immaterial. So expect contribution up to about 1 over square root of s. And then notice that this integral has an extra absolute value of y. In that region, it's dominated by 1 over square root of s. And that's why when you go all the way over here, you see that this error term is actually a 1 over square root of s smaller when you go through and do the analysis. It's coming from what regime do we expect the y to be contributing? We expect the y to be contributing up to about square root of s, and that's why that's coming into play. No, that's not. That's not flashing, so all right. Okay, so now we're down to just one last integral to do. We've got about 2 or 3 minutes. So if we look at this integral, we can write this integral as the integral from alpha to beta of e to the negative y squared divided by 2, and then we want to move the s and phi double prime downstairs. So it would be 1 over square root of s phi double prime of x naught squared. And I'm writing it like this so that you can see that this is a Gaussian. Now the important thing to note is that when we're looking at the contribution, if we went from minus infinity to infinity, what would this integral equal? If we went from minus infinity to infinity, well, the normalization constant we need is 1 over square root of 2 pi sigma squared. We don't have the normalization constant, so we multiply by the normalization constant and then divide by it. So we should expect that this should be like square root of so we have it would be like the square root of 2 pi over s, the square root of s phi double prime of x naught, which is exactly what we get from A. So if this was in minus infinity to infinity, we'd be done. So done if alpha is minus infinity, beta is infinity. They're not. But they're nice fixed numbers. And remember, s is going to infinity. Alpha and beta are fixed. So effectively, as s gets extremely large, we are so many standard deviations away from the mean of 0 that the contribution is just absolutely washed away. So even something bad like Chebyshev will eventually be good enough to kick in here and say that the contribution is negligible. You just need to trivially estimate what's going on if you're very large. And there's a lot of different approximations you can do. I wouldn't write it like this. I would keep it up like this. And then just say, well, look, eventually, no matter how small y is, the s times y is going to be at least 1,000. And so I could actually approximate this by an exponential. So if s is big, we have it as e to the negative sy squared will be less than or equal to e to the negative 1,000 y. Well, we've got to be careful because we still want to keep some of our s dependence, and so we may not want to go to something quite to that extreme. But what about just like e to the negative some constant times s times y? Can we do something like that? Can we somehow move a little bit and help out? Well, it all comes down to how can you estimate this integral? And there's lots of different tricks you can try. You can convert this to a gamma function. This is what the book is doing in terms of they go through an incomplete gamma function. I think you can just do this using Stirling's formula, not Stirling's formula, using Chebyshev. We can talk a little bit about this, next time. That if we are sufficiently far away, the exponential, and this is beyond an exponential, has so much decay. The other thing you can do is you can just change the variables as well and just write things out. So if people want, I'm happy to explain that in a little bit more detail next time, because we'll be doing Stirling's formula then, so we're going to do more on this on Friday. But I want you to get a sense of the key ideas of this. The key ideas is a change of variables to get it to a Gaussian. That's where the square root of 2 pi comes from. And then once you have that, then we just need our facts about the Gaussian to finish the argument. And that away from that, it's so much smaller because of the huge power of s that it just doesn't matter. Okay. All right.